Good afternoon from Blacksburg, Virginia. I'm Greg Vanilo from Virginia Tech and a co-organizer of this webinar series. Today's topic, presented by my colleague and co-organizer Gary Felton from the University of Maryland, will be water management and management of problematic feedstocks. As you have done in previous webinars, you will provide your questions in the Q&A, and most of them we'll address at the end of the webinar. However, if there are some questions requiring immediate clarification, I'll be monitoring those and make those known to Gary, and he can answer them as soon as necessary. So with that, I'll turn it over to Gary.
Good afternoon, everybody. We're going to talk today a little bit about water management, and then we're going to talk a little bit about how to manage problems, feedstocks that are likely to give you a problem. Problem usually means odor. We're looking at some presentations that were pretty well developed by Will Blacks from Sonoma Compost Company and Craig Coker from Coker Engineering. So I want to stop and say thank you to them. The content for this was developed out of the U.S. Composting Council Compost Operators Training course, or at least part of it was, and then I went through and edited it because there was a whole lot in that course. So why are we here in the first place? Why do we want to manage water? Well, obviously we'd like to be good stewards and we'd like to prevent water pollution. Not only that, it's required by regulations. The Clean Water Act, the National Pollution Elimination System, NPDES program, both of those require water pollution to be controlled. There are state requirements that make you do things for water pollution. And during construction, there's all sorts of soil and water conservation planning that has to go on. If you're in the West, water is a key process variable, one that's scarce and one that needs to be conserved so that you can use it rather than pay for it. Stormwater is a resource in the West. Sometimes it's a problem here in the East. So you have to look at it both ways. But it is a valuable tool even in the East. We have it for multiple uses here. What are the sources of water in composting? Well, we have run-on, which is water that's coming from some uphill place coming onto our site. We have clean stormwater from the structures, the covered areas, the roofs, and things like that. And we have dirty water that contacts our feedstocks, which we're not so wild about. Some of the water is called processed water. Processed water is contaminated stormwater or possibly contaminated stormwater. And it also includes leachate from materials. And finally, we have wash water for our trucks and other equipment. And that can be an irrigation source. The compost site water management idea is to use this resource, not make it a liability, manage it, and we have to kind of think about it in two different categories, two different columns. Is this facility in the arid West? If it's in the arid West, well, we need water as a resource. We want to save the runoff and the run-on. We want to recycle all the processed water that we can, or at least all that we need for our process. If we're in the East, well, it might be a liability. And we'd like to manage that runoff. We'd like to recycle what we can and what we need, but we're also going to want to manage the stuff that we're going to have to get rid of somehow. If it's not managed properly, this resource becomes a liability, and that's another word for lawsuit. So we have to be careful about it. And we probably will end up with an NPDES permit if it's a very large composting facility. We'll probably get that a little bit more. Let's take a little bit of a look. When you recycle water in the process, we want our compost to be about 50% moisture, but we lose water every day. The reason we lose water every day is compost generates heat. Heat causes evaporation out of our compost itself, runs right up through the middle of the compost pile and out into the air. So we've lost it. How much do you think we need to add? How do we decide how much we need to add? Here's an example of water in a compost pile. So if we look at a windrow And the windrow's 8 foot high and 16 foot wide, 200 feet long. From other things we've done, we can find that the volume of that is 632 cubic yards. We could do that with equations we have probably in one of the handouts we've given you or will give you. If the compost is about 100 or 1,000 pounds per cubic yard, which is nice average compost density, that's 632,000 pounds. If 50% of that is water, that's 316,000 pounds of water, or 38,000 gallons of water. Now, if we have a 1.5% water loss per day, we're probably in the arid west. Here in the east, we might have more like 0.5% water loss per day, maybe getting a little bit higher in the dead of winter when we have a good wind and it's very dry. But that 1.5% water loss would be 571 gallons per windrow per day. How many gallons are in a truck? Well, 1 to 6,000, depending on the truck. And the water loss at 1.5% per day is 4,000 gallons per week for the first 3 weeks, which means we may have to add water back or our compost will get too dry and it won't process properly. However, caution. We talked about compost or processed water once. I'm going to talk about it again. I'm kind of giving you the salesman's approach to teaching, which is I'm going to tell you what I'm going to tell you, then I'm going to tell you, and somewhere down the line, I'm going to tell you what I told you. So we'll talk about processed water several times, but you don't want to add that to finished compost because most places that will make that compost unsellable. When we incorporate water into a compost pile, this is one way to do it. This is taking a water truck, putting a crease down the middle of our water pile, and watering it into windrows. We put maybe 6,000 gallons in a truck it to wherever it needs to go, open up the windrow, add the water, turn around and close the windrow. This is another way to add water. This is out in Sonoma, California. This is a horizontal chipping operation, and the water is added to the compost before it's even made into compost. It's added to the chipped product itself. And if you look at the top, there's a bunch of water nozzles, and they're shooting out as the chips come shooting out of the conveyor. So this is one way to add water. Probably one of the easier ways to add water is to do it as part of a standard process. This is another way to add water. Uses irrigations. These pipes have emitters in the pipe themselves. If you look at these little spots along here, the spots on the pipe are probably an emitter. We'll look at a closer view of that in just a moment. This is drip irrigation, and this is done at the Sonoma compost site also. These emitters, which you can see 2 of here at the 2 extreme sides of the pipe, put out about 1 gallon per hour. And you can get them in 1/2 gallon, 1 gallon, 1.5, and 2 gallon outputs. This pipe comes on long reels, and you can just lay it down. With 4 lines, you're applying about 4 to 5 gallons per hour for every foot of that pipe that you put out. So at 200 foot long, like the windrow was, that's 3,200 to 4,000 gallons that you're adding. That means you got to have a supply line that can add 4,000 gallons in a reasonable period of time, for instance, 6 or 8 hours. It takes 4 to 5 hours for water to go from that irrigation pipe to work its way down through the pile to get down as far as the bottom of the pile. So we're going to have, you know, a quarter of a day for water doing what we call redistribution. One of the things that works better than most other systems is something that's integrated water systems integrated into the compost turner. All of these are compost turners. This first one up the top is a tow-behind compost turner. The other 2 are self-propelled compost turners, and there's a water line that goes to that. We even have one self-propelled little compost turner that just pulls a water tank off to the side. But that's kind of an awful lot of stress on some parts of the turner itself. These 2 bottom ones show how a water reel is attached to the compost turner. So those are the ways to get compost into something. We want to look now at stormwater itself. And stormwater is the rain on the roofs, the pads, the piles. It's the rain that falls down. It could be surface run-on, and the stormwater is the surface runoff. If you rain on a compost pad, not all of the water comes off, so the surface runoff is less than the rain that falls on it. So just how much is that, and what should you plan for? There's several things that determine what makes runoff amounts. One is the rainfall, obviously. You can't get any more runoff than what you put on. The surface features of the compost site, which might include the materials that you're using. The fresh turned compost takes up water pretty easily. Once it's been rained on, it seals off better and sheds more water. The area of the site controls how much total volume comes off. Also tells you how long it's going to take before you're seeing the maximum amount of water. And there's all kinds of regulatory requirements that control this. Okay, what are those requirements and how do we handle them? In precipitation determination, really ought to call this precipitation estimation because we don't know exactly what we're going to get. I encourage you to get some help. Most likely, somebody is going to be able to do this calculation for you, but if you do it wrong, it's probably a liability that can come back to bite you. The NRCS field office can help you. If you have small areas, you probably won't need all the permitting, but larger areas do. So larger sites are probably going to need a professional engineer's stamp on it. Each state will probably have different requirements. But this is handbook engineering, and the results have legal implications, so you really want to get help on it. Rainfall varies in both time and space, so we often see storms that run up and through a compost site, or they may run across the compost site. That's going to change the amount of rainfall, both in how long it takes to get across it, and also in how much can fall in a space where if the storm is small. Rainstorms are what we call design storms. They're described by a couple of things. One is called the recurrence interval. An example of that would be either a 10-year storm or a 25-year storm, where we would have a probability of it occurring once every 10 years or once every 25 years. And those are called the return periods. And there's a relationship between that and the probability of it occurring in any given year. It's defined by statistical frequency analysis for your area, and so it's defined all over the nation differently. My 10-year 24-hour storm here in Maryland is just under 6 inches, but a 10-year 24-hour storm in Sonoma, California is a little closer to 3 inches. The 10-year storm has a probability of occurring once every 10 years, or 10%. That's 1 over 10. A 25-year storm is likely to occur once every 25 years. That's 4% for each year, or 1 over 25. And there are data tables available from NRCS, from NOAA, from other sources. The website down here is where to get data tables from NOAA, and those tables are available for pretty much any part of the country, I think every part of the country. Hello. There we go. When we talk about runoff prediction, again, maybe I should be saying runoff estimation, we use models to predict runoff. The simplest model is called the rationale method, or some people call it the rational method. I learned it as rationale. It gives a peak flow rate. Doesn't tell you the total flow, it just gives you the peak flow rate. That's useful when you're designing structures like culverts and dams and things like that. C is a runoff coefficient, and it's a number that is associated with the land. I is a rainfall intensity, and you get that from the rainfall prediction, and A is just the watershed area. This particular equation is typically used for smaller watersheds. It would be very appropriate to use for most compost sites. We have a big compost site here in Maryland called the Dickerson plant. It's got 55 acres of compost pad, so I would use a different method for it. But where we're talking about 2, 3, up to 6 acres, the rationale method is fairly useful. The second one is the NRCS runoff curve method or curve number method. The curve number method was developed so long ago that it was originally called the SCS method, the soil conservation curve number method. It's used in larger catchments. If you see computerized models for runoff, most of them you're using the NRCS curve number method. It gives peak flow, and it also gives total runoff volume. The key is to develop a curve number, and we develop curve numbers for different land uses. We develop curve numbers that have conservation treatments, hydrologic condition, wet or not wet, and soil drainage characteristics. There's something called TR55, also known as Technical Release 55. It's a piece of paper, but it's also the terminology used for computer models. There's a website down here. It's www.l, that is a lowercase l, MNO Engineering. And in this is all kinds of hydraulic calculators, including the curve number method. So you can find something and try to work with it from this for free. These are runoff coefficients for the rationale method. It talks about the type of drainage area and the coefficient. When we're looking at streets and asphalt, the coefficient is 0.85 to 0.95. If it's streets that are concrete, it's 0.90 to 0.95. And if you think about that, asphalt is a little bit porous, concrete is a lot less porous, and what we're seeing, these numbers on the right-hand column, are essentially the percent of rainfall that it gets converted to runoff. So when we're taking a look at a gravel area, the bottom line here, we're saying that 25 to 50% of the rain that falls will end up running off of a site, whereas up here with concrete, we're saying 90 to 95% will run off. In the larger model, in the SCS curve number method, or TR55, curve numbers come up from a land use. So we see paved parking lots, streets and roads that are paved, gravel, and bare soil. And then we have hydrologic soil groups over here. There are other divisions of these rows across for different conditions of the soil, whether it's wet or not wet, but we haven't included those in here. So we're just going to look at the soil characteristic where we have these letters A, B, C, and D. And these tell you how well it's drained. A type A soil is a very well drained soil. And if you look up in the soil survey, find the name of the soil that you're on, it will have a hydrologic soil group in one of the data tables in the soil survey. And type D is a 98 for the same area. So if we look across paved parking lots, routes, driveways, doesn't matter the soil type, we're saying that 98% of the rain that falls will end up running off. If we look down at the bottom where we have bare soil, we're saying that in hydrologic soil group A, which is well drained, 72% of the rain that falls will end up turning into runoff. We look at the other end of it, hydrologic soil group D has a curve number of 89. We're saying that almost 90% of the rain that falls is going to end up as runoff. We have this term process water. I've mentioned it once, here it comes again. That's water that has been contaminated in the compost process, or water that has touched the feedstocks, the active compost area, or has been exposed to high traffic areas and other sources of contamination. We want to minimize processed water as much as we possibly can because it has to be treated, and treatment means money and time. We want to minimize processed water by putting a roof over raw materials if that's feasible. Not every operation can afford one. We want to put a diversion around our pad just about all the time. We want any water that's flowing downhill towards our compost area to run around it rather than through it. We want to locate the feedstocks and the active compost areas away from the finished material. This is not because of the process water action itself, but because we don't want the processed water to get into the finished material, because then we'll have to retreat it. And retreating compost is a lot harder. All the carbon's been used and it won't compost well. So this is sort of the hierarchy that we like to use. We like to first reduce the amount of water we have. Failing that, or what's left, we want to reuse what we can. We want to recycle more of it if we can. And last, where we have to, we do have to treat water. And we'll talk about treating water further down the road. We want to separate the clean and the contaminated water from each other. We want to keep feedstocks and active compost downstream or off to the side, some way isolated hydraulically from everything else. We want to put on roofs and covers where we can. We want a grade separation so the water flows from one area to another area. We want to put in vessels that reduce or eliminate contamination. Some of these might be forebays that allow settling to occur. And we have to prepare for emergencies and extreme events. If you do a design for a 25-year, 24-hour storm, which is what a lot of structures are designed for if there's no life in danger, you still got a good probability of seeing a 100-year storm sometime during the life of that compost facility. So you have to think about, well, what's that extreme event going to do to me and how am I going to handle it? We have water storage techniques. One of them is called a Baker tank. Others are bladders. These are being used in not only compost work, but in some sewers that have a lot of runoff going into the sanitary sewer that they really had combined sewers and are now using tanks to kind of lessen the runoff. We have treatment that we need to think about. We have to get as much data as we can and the approvals necessary before we start doing building. Finally, we get to look at something like this, and this is what we're trying to avoid. We want to avoid compost piles sitting in water where they're going to soak up all that water. The compost is going to become saturated. We can't sell it. It's going to turn anaerobic, and we're going to have odor issues. So whenever we get water or get wet compost, we run the danger of having odor issues. That's the quickest way to shut down a compost site. So our site design and management is to prevent runoff. We use that with berms, swales, diversions, some sort of structure. We want to direct the runoff away from composting feedstocks. We want to have a minimum of 2% slope because it takes that much to really make water run on a hard surface in a way that can be directed. Little tiny imperfections in a paved surface can redirect water on less than 2% of a slope. We want to direct runoff to infiltration ponds or storage ponds so that that water goes into the soil and we don't have to manage it as surface water. One of the things that's the management component of this, our pads have to be firm and smooth, and that's a maintenance issue, particularly if you don't have some sort of asphalt or concrete pad. It means you have to inspect those pads and you have to perform repairs on a fairly regular basis. These are some cross sections. This is a cross section across the compost pad from runoff diversion to the pad dike that keeps runoff from going onto the pad, to the dike on the other side that keeps runoff from coming on that way. And so this is looking up and downhill. Where we look sideways here, runoff diversion channel, this is what catches runoff from uphill, and it'll run it around and down through one of these channels. The pad length and the windrow pile length need to be at a 2 to 4%, even 5% slope. And the pad runoff collection is a channel. You may have a holding pond, you may have an infiltration area, something that takes the water that comes into this runoff collection area, into this diversion uphill, runs around the site, and then infiltrates into the ground so that you don't have to manage it as surface water. When we're designing these things, it's far easier to manage our runoff than if we're trying to do it after the design is put into concrete and put on the ground. So the design considerations we think about are high contact areas we want to drain to a separate location. This is the process water. High traffic areas where our trucks come in, trucks go out, maybe where we park our equipment, we want to drain to an oil and water separator because that water is going to have oil in it no matter how well you keep your equipment in case. The fresh material coming in from the feedstocks, we want separated from our finished material. We want to keep, that's the third time for that. We want to keep them separated. A great deal of daily water management is dictated by the original site design. So we really want to design to minimize water management problems. That design is something that you probably need help for if it's a large site. If you're doing a small site, you want to keep all of these things in mind. If you, for instance, are working a farm site that's going to be growing into a compost site that ends up being commercial. So where you can, cover it. You want to cover the receiving building and keep all of the feedstocks in the building under cover so that you don't have runoff from it. You want to look at the truck washout area so that you direct that to a holding pond with high strength water and probably to a oil and water separator. Here's another design consideration, a sweeper truck. This is a way to collect material before it gets attached to water so that it doesn't become something that has to be treated. The fines that you generate in composting very quickly can clog up things. So keeping them out with a sweeper truck gives longer life between maintenance. Fines build up in channels in spaces between the compost piles, at the end of the compost piles, someplace where the water has changed velocity and lets stuff settle out. When we're in different areas, particularly in humid areas, we need to shape our piles so that they're crowned. The crown at the top there makes runoff go over the pile and down rather than into the pile. If it's a flat pile, you end up getting water in there. In the humid region, you end up getting too much water in there, and you have anaerobic conditions, odors, and you can't sell the compost, and you can't really manage it either. This is what it looks like at a 2% slope. So in case you're not sure what a 2% slope looks like, this is a 2% slope running from the piles towards the greenery on the left. It's not all that steep. It looks almost flat, but not quite. And this 2% is what's necessary to get water to run sort of in a straight line on a hard surface. This is a picture of a site where there's a grass-lined stormwater ditch at the foot of it. It collects and prevents run-on, and it captures runoff. This is a different design. This has a pad depression along the middle of the facility, and so water runs from the front of the slide towards the center and from the back of the slide towards the center to a center channel that collects runoff, and then that channel itself is sloped downhill from left to right. This is the channel that collects water. It drops down these several large hills and then goes to a collection site. This is one where you have the luxury of reshaping the earth before you build your compost pad. Infiltration is a real nice method for treating things. It's a very common, simple, inexpensive option for some process waters, and that may vary from state to state whether you're allowed to infiltrate your process water. You use something that's called a level spreader to get the water into the infiltration area without having concentrated flow, without having channels. You use grassed or vegetated areas to make infiltration strips or infiltration basins where it collects the water, holds the water, and lets it infiltrate into the soil. There are also biofiltration systems. Those are similar to rain gardens. They might be rain gardens. They might be bioswales, which we'll see a picture of a little later. But all of these use physical, biological, and chemical processes to treat water. There's physical processes such as plain old filters, biological processes where the microbes will attack some of the matter coming in and digest it, take the carbon out for energy. And then there's chemical processes where some of the infiltration areas may be treated with crushed concrete, which will raise the pH of it if pH is an issue. This is a spreader. This is a PVC pipe that's stretched along. They used a level to set this in place so that it's the exact same elevation all along there. And water collects on the right-hand side of that and will run over that pipe in a uniform flow rather than in a concentrated flow. This level lip spreader is a best management practice, or a BMP. And so you'll see these where a lot of water is being treated, but it can be treated in an infiltration channel. This is a different type, but still is an infiltration basin. If you look closely in the middle of that basin, there's a drain area, and that's a pop-up drain for when there gets to be too much water in that basin, and it draws it underground to another basin, a secondary basin. That riser is in case of a lot of runoff. In this case, this is up at Penn State, where they have their food waste and yard trim compost site. This one almost never fills up with water. The secondary basin has never been filled. It has had water in it, but it's never been filled. One thing you might want to take a look at here, on this same area in a different season, fines are collected right where the pavement ends and the vegetation starts. So this vegetation area and the change in slope and the change in roughness all make the fines settle out right here at the start of the best management plan, or the best management practice, which in this case is a filter strip. This is the fines collecting here. This is a bioswale, sometimes called biofiltration. It is mostly vegetated. The center channel will vegetate or not vegetate, depending on how long water stands in it. But that material there is made to be fairly permeable so that water can get into that channel and then slowly infiltrate down. That collects the water, holds the water. It has an overflow at one end, so if it gets too much water, it won't break through the dam, but rather will be routed around to a basin below it. The next thing we think about in this water are solids. And so we have to do some solid separation. And in fact, solid separation ahead of some of these infiltration treatments is probably your biggest bang for the buck. It keeps stuff from clogging up, reduces your maintenance, makes it so that you can spend more time working the compost, which is where your income's generated from. The compost filter berms or tubes, such as made by Filtrex, are one of the simpler solid separation methods. Forebays or chambers or sinuous channels are also a solid separation method. And the utility of these depends upon the process water storage facility design. So different ways of storing water may depend on whether you should be using berms, tubes, forebays, chambers, or a more sophisticated separation method. Here's a simple method. There's nothing to this but a pile of chips. This pile of chips is at the toe of the pad, so all the water that comes from the compost piles goes down into this first. This pile of chips will get changed every few years probably, and they can be put right back into the compost operation as part of the bulk material that goes in, or part of your organic matter that goes into your compost mix. And just bring out more chips that you normally get anyway. Very easy to maintain. You just put it down, walk away from it, and check it every now and then. These are just mulch or chips. There's a couple different things we're seeing here. This on the left is the finished compost being used as a stormwater filter in a berm. That red hose on the left is filling this compost sock. This is a Filtrex technique to build one on site where you need it. On the right-hand side is a chipped berm. That chipped berm is leading to an underground sewage system, stormwater system. These stormwater systems are subsurface. When you go subsurface, you pretty much are guaranteed that you're going to go into an edge area where it goes anaerobic eventually. There'll be a lot of organic matter down there, and it will use up all the available oxygen. Also, periodically, it creates clogs. That's an irritation. But when it goes anaerobic, if you have enough organic matter, you can end up getting basically sewer gases down there. And so you want to be very hesitant about letting any workers go down into this subsurface drainage area. It can be a confined space with hazardous gases. You can get hydrogen sulfide in there. It has happened at a couple of compost sites, and people die. So please think 2 or 3 times before allowing any worker to go in any subsurface drainage area. Okay, off my soapbox, on to solid separation. These are all solid separation technique prior to retention basin. So what that means is that this is a porous pavement here on the left. You can see the fines that have settled out. It's going to flow from the grassed area on the left to the pond on the right, and it's going to flow over that dam to get there. So you can see that's quite a step up, and we can take a lot of ponded water there and hold that ponded water while it infiltrates. Once it infiltrates, then it doesn't become water that has to be treated. On the right side of the dam, that water is going to have to be stored and treated. So this porous pavement is one way to treat water so that you don't have to put it in a treatment system. This is a more sophisticated system. I think this system is down at Cedar Grove in South Central Virginia. Here, Filtrex socks, these large black socks, are filled with rough compost. They're placed across the opening to filter water, and the water goes into the pond much cleaner. This is also an HDPE, high density polyethylene liner. With that kind of thing, you can't use heavy equipment on it. So you've got to clean the fines out before, because cleaning this out once the water gets in there and settles is going to be a very difficult task. The other problem with this is you can't allow deer to get on it, because deer will puncture little tiny holes all over this HDPE, and you'll have to go in and replace it, which is an expensive and irritating thing to have to do. So you have to think about deer control if you have high density polyethylene. This is a 4-bay solid separator. This solid separator takes water in, runs it sinuously back and forth through stilling areas, and it goes out the pipe at the far end. This kind of illustrates the pathway where it goes down from one area into the first bay and works its way through. To the left of each bay, you can see a sloped area, and that's designed so that a front end loader can get in there, scrape all the settled fines out, take it back, mix that in with the compost in a new compost pile. So this is designed to be maintained well. This is a simpler one, just recycled straw and sediment. This is a rock wall sediment trap. At the end of this water, right next to the green area, is a rock chip and that dam allows water to flow through it slowly, so it backs water up, which allows solids to separate and to drop out of suspension. Retention basins are commonly sized for at least the 25-year storm. There's also a design property built in called freeboard. If we're doing retention basins or ponds, essentially the freeboard is typically 1 foot. So there's a lot of extra storage in that freeboard. Proper design is necessary. You probably want to call in some help, either NRCS or a PE, one of the two. Excuse me. There are local codes, there are regulations that apply. So when you design one of these, there's a lot of regulatory oversight. There may be separate basins designed for contaminated and non-contaminated water. And once that water is collected, it must be treated or used, or at very least what's called managed well, depending on the state regulations. I strongly urge you to get help for the designs of these unless it's really a small structure. This is just a simple stormwater retention pond. It's used as a water source. If you're in an arid area, you want to collect the water, and you may use that water to put it back on your compost site. I visited one compost site in West Virginia, which is very much a humid area, but they irrigated water back onto their compost because the entire compost site was under roof. And so they had hard risers built in place that were permanent, and irrigation was done on the compost as a regular course of the operation. This is a facility that shows separate ponds for both contaminated water on the right and regular storm water on the left. Those two little ponds in the middle there. This is Cedar Grove in Everett, Washington. This facility has stormwater treatment and process water treatment. And you can see at the bottom there, those white spots in the dark are oxygenation, where water is pulled from the bottom of the pump or the bottom of the pond and pumped up into the air so that it goes through the air and gets oxygen in it. That brings us to what do we do with the processed water? What are the treatment requirements? Well, first and foremost, if you have processed water and you need to treat your active compost piles, then you can use that to treat the active compost. Processed water can be used as dust control. That's one of the problems that are in the arid west, that they have to water down the dirt roads pretty much daily. It can be used off-site. If you have crop areas available to you, processed water can be used for irrigation, and it actually provides a little bit of fertilization. Not very much, but some. Aeration can be performed on it. That aeration affects odor control. You get more odor control when you have oxygen involved. You reduce the odor. There's treatment options. An on-site system, we saw one picture of that in the Everett, Washington site. Or you can send it to an off-site facility, which is really expensive. And you might want to keep that as a contingency and an emergency, but it's not something you would want to do all the time if you're trying to make $1 on this. It's economically usually pretty tough. You look at this slide, and what's in that processed water? Well, the possibilities are everything. Where we have BOD and COD, that's biological oxygen demand and chemical or biochemical oxygen demand, actually, and then chemical oxygen demand. These are two different methods of measuring the ability of the stuff in the water to pull oxygen out of the water. And most areas have regulations about water with high BOD and COD not being released. There's nutrients in the water. There can be metals in the water. There can be salts. We almost always get a certain amount of turbidity that's just due to the tannins that are in the compost material coming out and getting into the water and making the water dark. There can be pathogens. Even if we have pathogen treatment in our compost process, the areas on the site that are not in the active compost area certainly have birds visiting them and other things, and we end up with pathogens in some of our stormwater. Usually not high amounts, but some. Depending on what you're getting in as feedstock, there can be pesticides, herbicides, pharmaceuticals, you name it, it can be in there. It doesn't necessarily mean that all of this is in all of your processed water, but these are some of your possibilities. If we look at this chart, this is the ranges that can be found from lots of different water samples. The BOD range is from 20 milligrams per liter up to 3,200 milligrams per liter. On the right-hand side, for some of the metals, we see arsenic from 0.001 up to 0.04 milligrams per liter. Some water, if water comes out of the ground, it can naturally have arsenic in it. If we look at fecal coliform, which is most probable number per 100 mils, look at the range here, between 200 and 24 million. So if we're going to look at fecals, it can be almost anything, depending on what the facility is, what the compost feedstocks are. Some of the metals, copper, zinc, those metals have a fairly narrow range compared to some of the other things, but they may have to be treated. pH can be 6.7, which is fine, but 9.5 is usually too high a pH to be released. There are regulations that may be as low as 8, maybe up to 8.3, 8.5, depending on local regulations. If we look at conductivity, if you remember, conductivity is also a measure of salts that are in the water. So when you have 887 milligrams per liter, it's not very high conductivity. Woo. Is that you, Greg?
I wanted to jump in here and ask a question, Gary.
Greg, you're getting a little bit of, real quick, we're getting a little bit of noise from your, I think it's either rubbing on your shirt or maybe something else weird that's going on.
Okay, am I coming in all right?
There we go.
Yeah, I was just say, as long as you don't move, when you move your head back and forth, that's
okay.
Where the noise goes.
All right, I'll be perfectly still. So a question that came up, Gary, with all these processed water parameters is, what are some of the factors that would determine the amounts and maybe the types of these parameters you'd have in your water?
Good question. There's basically two things that go into compost: feedstocks and water. And so in almost all cases, this will come from one of the two. What's in your feedstock? Well, if you're composting biosolids, you can get nutrients in there. There can be a little bit of lead in there, a little bit of copper. If you're composting something and you're using well water to do it, you can get arsenic in it. If you're composting materials that have lots of phosphorus in them, something like that could be chicken litter. It can be pretty heavy in phosphorus. You get a lot of phosphorus in the processed water, depending on how you compost it. What would chloride come from? It comes from a salt. You're going to find that salt is in the compost feedstock somewhere. And sometimes that comes out as a natural decay process. Sometimes it's something that's introduced. If you get chicken litter, you will often get potassium salts as well as phosphorus. So you can get the sources from your feedstock, or you get it from the water you use. But that's pretty much the two places. There is one place we're looking at right now where over the years the pH has crept up from about 7.5 to about 8.3. It may be that the pad itself is wearing away and it's getting more carbonate from rocks in it and possibly from crushed cement getting into the compost and raising the pH. So the sources are not usually the pad, but quite often the feedstock and occasionally the water. Sir?
Sounds good.
We'd like to recycle that stuff. We'd like to take that water and use it for something on our property. Maybe we could work with a nearby farm operation and use it as spray irrigation for crops. We can use it for row crops, for pasture. Turf grass loves water, and we can just generate biomass. There's becoming more and more of a market for biomass, so growing switchgrass with irrigation is not something that would be unheard of at some point in time. We can use that material or use the water and apply it as overland flow, which is what we call furrow irrigation, or basin irrigation. Those are two names that are similar. We can do spray irrigation, which is the standard irrigation that we see around here. Drip irrigation, which is much more conservative of the water, but you have to be careful when you do drip irrigation with processed water, because those little tiny drip outlets clog. The emitters can clog up pretty easily, and processed water has a lot of things that can clog it up. So a lot of times drip irrigation water goes through a sand filter before it's applied. If you have a sand filter in with processed water, you're probably going to clog that sand filter up pretty quick. You can also use subsurface irrigation galleries, something like corrugated drain pipe that's running under some soil, and a lot of water is fed into that, a little bit similar to a drain field from a septic tank. Normally, we design these things for a hydraulic loading, but they might also be subject to nutrient or salt management planning. Hydraulic loading says I can put so much water on before I'm starting to change properties. Well, properties of what? Properties of the soil or properties of the drainage field itself. If we put too much organic matter into a drain field, it can develop a layer of organic matter that doesn't drain well and clog the field. Sometimes when we do this, we have to pre-treat to disinfect. Sometimes the lack of disinfection may influence the setback from the property line, how far back you can treat water away from the property line. And so that limits the value of the property you may have to purchase. How do we treat it on site? We use structural BMPs as one technique, and that's where we use it to manage both quality and quantity. One of the structural BMPs is a settling pond. The other one, that 4-bay sinuous path settling area, is a structural BMP. You need to have regular maintenance on these. You've got to be able to pull the material out that you settle out and take it back to the compost operation. We use BMPs that can handle nutrient loading and that reduce the BOD and the COD. Typically that means adding oxygen to it somehow. Usually aeration. We don't actually buy bottles of oxygen and inject that. These are usually some sort of vegetated solution, which are simple grass waterway or grass buffers, rain gardens, bioswales. Could be a wetland, a treatment wetland. We can also use multiple types in series. So you might use a structural 4-bay to get most of the solids out and follow that with a bioswale that would drain into an infiltration area. So you could use 3 things in a row to get a lot of treatment and end up just infiltrating your stormwater. We're getting there. Not getting there fast enough. What are some of the complications? The amount of treatment. The biggest thing is regulatory requirements are going to give you the biggest complications. Secondary treatment is required at a minimum, and that says you have to bring BOD down to 30 milligrams per liter, total suspended solids down to 30 milligrams per liter, total N and total P down to these limits. Tertiary treatment might be necessary in nutrient-sensitive waters, where tertiary means we're going to have to, by some method, take some chemicals out of the water. We can use settling treatments for phosphorus. Nitrogen's a little bit tougher. We probably have to go through some anoxic conditions and then go into an oxygenation section. And we try to do flow equalization of some sort. That's a structure where the flow is going to, your input ebbs and flows, but you want the flow through the treatment sections to be fairly constant. That can be as simple as a standpipe in a pond that will only let so much water through. So what are the pollutants and what are some of the associated treatments? This is a table, and I'm not going to read this thing to you, but these are the treatments that are associated with different water pollutants. And so we use, down at the bottom, we use precipitation for metals. We use precipitation for phosphorus. Going up, we use biological conversion. And when we have B&D and COD, we use aeration. So that's kind of the range of the things we do. And we can have to use almost all of these in some situations. What are the efficiencies? You know, we don't know that very well. I mean, we look at them and we get efficiencies from different things that we measure, but they are so variable, and each compost facility is sort of its own prescription, that we have some evaluated with respect to nutrients, solids, and metals. There's a BMP database, but we really need more data on this. There's some data talking about bacteria removal, but not a lot, and there's very little on BOD, COD removal, and certain chemicals called tannins and phenols. So we have sort of a lack of data for our removal efficiencies. Some of them that have been around for a while, like solids, we do have some data on. What's expensive? What's cheap? Well, the lower cost things are compost berms, solid separators, infiltration systems. The more expensive ones are totally lined ponds, ponds aeration, multiple units in series, or treatment trains, they're sometimes called. So, what does a compost site process water management develop for issues? Stormwater management's important. Compost operations have to have it almost on a daily basis. It's a regulatory obligation. We have to recognize the realities of composting and the potential water impacts. We need site design and management both. Both of these are things that you need to do because a good design will reduce the amount of management you have to do every day. Well thought out plans for managing. We have to think about what's normal, what's the expected rainfall, and also what do I do in extreme events. You have to have some thought of what you're going to do when it goes beyond your design capabilities. Something will overflow sooner or later. Don't forget the order we like to do things in. We like to reduce, reuse, recycle, store, and treat, and finally, where treatment might be infiltration. Stormwater is a resource. Use it. Don't buy anything if you can avoid it. Okay, at this point, we're going to switch a little bit. Greg, have you seen any new things there? Any questions? It'll take me a moment to juggle these things around.
There are no other questions that have been asked in the meantime.
Okay.
If anyone wants to type anything in while Gary's making the change, but again, we will have time at the end.
Greg, do you see my screen?
Yes.
All right.
Go ahead.
Okay. This is a completely different topic, except that it still includes management. When we have problematic feedstocks, there's something inherent in the feedstock that means you're going to have a problem dealing with this thing. And I hope you all don't have a problem dealing with this one because it's a short presentation, I promise. What are the elements of successful composting? Well, we get the C to N ratio right. We get oxygen right. We get the moisture right, pH right, and the temperature. Sometimes these are called key process variables. These are what makes composting work. A problematic feedstock is something that impacts one or more of those elements, and it throws the system out of balance. So that's a nice generic description. The C to N ratio out of balance. Rarely do you have too much N, but if you do, you'll know it as ammonia off-gassing, and you'll get a lot of ammonia. And so that could be a problematic feedstock that causes that. Too much carbon results in not much microbial activity. You get low temperatures, slow composting. Well, if you have too much carbon, you may also get it so slow that you can maybe get putrefaction instead of composting. If you're composting only leaves, not much happens. It's all carbon, almost no nitrogen. If that's the issue, co-compost with something. Well, feedstock that's higher in nitrogen might be grass. It might be food waste. So there's possibilities of other feeds that you can mix in. If oxygen is restricted, then we begin to get issues that can get us shut down. If there's low nitrogen, then there's low microbial activity. There's low temperature, and there are anaerobic conditions. That means you need to get oxygen in there. If there's sufficient nitrogen, then anaerobic decomposition can occur. And that we call septic tanks, basically. So anaerobic digestion creates methane, it creates CO2, and these little trace gases, aromatic gases, sometimes called stink. The best example of that is hydrogen sulfide. Hydrogen sulfide is that rotten egg smell that you get with swamps. So if that's the case, you need to use some sort of bulking agent to increase the airflow. And you got to do that fast if you notice that odor. When you turn that bulking agent in, you're going to get a release of odor. So you probably shouldn't turn that bulking agent in at 5 o'clock in the evening when everybody's coming home. You want to think about the timing of that. If you have a moisture problem, if it's too low, obviously you add water. But if it's too high, you can't subtract water. Your choice is to use a bulking agent to increase the airflow, or let the feedstock dry out before you put it in the compost process. One example of that is aquatic weeds from an urban pond maintenance. In Columbia, Maryland, they have several 6 or so acre urban ponds, and the weeds hand over fist. They have actually contracted and purchased a pond weed lawnmower where it cuts the weeds off and collects them. Well, to compost those things, they have to get a lot of something else, bulking agents. This is what the weeds look like on a pond, and this is where they compost them, and this is before compost, so this is just the raw materials. That stuff's soaking, sopping wet. You can see from the green it's got nitrogen in it. They have to mix this with a lot of carbon to avoid having an odor problem. If you have a pH problem, that usually comes in from your raw materials, from your feedstock. This feedstock on the right has a pH of about 12. If you look at those white dots, those are lime dots. And this is lime stabilized biosolids. From Blue Plains, this stuff comes in with a pH of roughly 12. If it's too acid, you can add lime. Otherwise, you get dead microbes. Dead microbes mean it's going to probably get kind of odorous and anaerobic and stinky. If it's too basic, again, the result is the death of the microorganisms, and you need to use a bulking agent that has some buffering capacity, and you're going to need to dilute. So this particular biosolids material was diluted with a 1-to-1 mix of chipped pallets in order to get the pH down to where it would compost.
Gary, if I could jump in here quickly.
It's your favorite topic.
There was, well, not about that topic, about a question by one of our listeners who's a little confused about what you said. His interpretation was you had mentioned high nitrogen causing anaerobic conditions, where his understanding from what you said previously was it would be caused by high moisture or low porosity. So could you clarify the relationship between high nitrogen and anaerobic conditions?
If there is high nitrogen, it's another way to say there's low carbon, but it's not necessarily anaerobic. Something else could cause it to go anaerobic, like moisture. It could be packed too tight. So it's a combination of two conditions. Plenty of N, but for some reason there's not enough oxygen getting in there. And that'll cause methane and aromatics. So that,
yeah, I think also possibly your point about nitrogen compounds demonstrating that you have anaerobic conditions by, say, an odor of a reduced nitrogen compound like ammonia.
okay, yeah. And that would be a symptom. The nitrogen smelling like ammonia, or the pile smelling like ammonia, is a symptom of having nitrogen but having anaerobic conditions. It's not that one causes the other. The anaerobic conditions cause the ammonia, but the ammonia doesn't affect the anaerobic conditions. In other words, is that correct?
That sounds good.
Okay, let's see if I can find out where I was. Yeah, finish this. Okay, some problem feedstocks might be fish waste, butcher waste called offal, something called DAF. DAF is dissolved air flotation waste. That's something that's done in food processing, where they have something that's very wet. It is a liquid, in fact, and in that liquid is suspended solids and fats. And they put air in at the bottom of that liquid in very small bubbles. They bubble it in, the air floats up through the liquid and attaches to some of those waste particles, creates a scum at the top, and then that scum is taken off with a skimmer, and that becomes DAF. That stuff is frequently in food waste or in food processing operations, and it's a waste that needs to be gotten rid of, but it's hard to manage. And finally, another problem feedstock is municipal solid waste, the organic component. So we'll go through all of those. This is a fish waste from a fish cleaning operation here in the Washington area. This fish waste comes in a fish cube where the skeleton and the guts of the fish are all thrown in a tank. The tank is frozen and the sides are taken away, and that block of ice then goes out to be managed. It's got a high water content. That means there's a good probability that anaerobic conditions can end up happening. It has a real high odor potential. There's a lot of fat in there, and the fat can end up going putrid very rapidly. So one of the things you'd like to have is rapid thermophilic composting, where we get plenty of heat, but more than that, we get lots of microbes reproducing. And so you want to use some active compost as part of the cover, which jumpstarts the process. So you would have a pile composting. When you make a new compost operation with this waste, you would use some of that composting material, still hot, to mix in with your fish waste. You want to make sure you have plenty of chips, plenty of bulking agents. A low airflow gets anaerobic conditions and that famous rotten egg smell. If we look at butcher waste, this is butcher waste off of a actually fairly small butchering operation. It's similar to fish waste in a lot of its properties. It has a high water content, not as high. It has a potential to layer and make airflow difficult, so you get the airflow problems. And because of those, you get a high odor potential problems, and obviously it has a lot of fat that can go putrid. So again, we need rapid thermophilic composting. So use active compost again. Again, use the chips and the bulking agency or bulking material. Another thing you want to worry about with this is you want it blocked off and fenced off so that you don't get varmints coming on and uncovering your compost and allowing it to rot instead of compost. So you want to keep things like buzzards, fox, raccoons from getting anywhere near your compost pile. That's quite a problem sometimes. This is the general problem with anything that might be meat. A dead chicken in a compost area will get dug up by the neighbor's dog, and that neighbor will proudly take that dead chicken home to its owner. That will give you some kind of neighborhood problems. This collection of bald eagles is a fish waste issue up in, I think it was Fairbanks, Alaska. I'm not sure if it was Fairbanks or some other area. But this is a fish waste that's been dumped instead of composted. This is stuff that they pulled out of what was ostensibly a compost pile, but it drew eagles. I've never seen that many eagles anywhere else. The DAF waste is a little bit unique, but since there's so much of it, I wanted to talk about it. It's got water treatment processes. It's due to water treatment processes. I've described them. The released air forms bubbles and scum, and you get a sludge. That's how it's made. What do you do with it? Well, it's got a high liquid content, very high. Has very high mobile nitrogen content. Let me explain that a little more carefully. The nitrogen can get into the groundwater. It can run right out of the bottom of any compost operation if you're not careful. My advice is to avoid DAF in your compost operation because it has a bad reputation in regulatory circles. If you're going to compost it, you have to contain that. One way I've seen it contained is in a concrete pit that had a sloped side where a front end loader could take front end loads of chips, put it into the pit, mix them up until it was no longer dripping water, and then carry them off to be put in a compost windrow. But they had to mix it in the concrete lined pit to contain the DAF. So that pit was built specially for disposing of DAF in a compost operation. MSW, municipal solid wastes. There are some things called MRFs, which are materials recycling facilities, MRF. And they put out this stream of organic matter. The problem with the organic matter is it's got contaminants. And this is a pile that was developed somewhere down in Florida, is all I know. And this organic material is just full of things that aren't compostable at all. So whatever you do, you're going to end up with an awful lot of materials that are just trash. And that's probably the biggest problem with municipal solid waste. Now, we have problems with trash getting into our feedstocks in all composting operations, but this is just inviting regulatory purgatory. So that's the end of the talk about problematic feedstocks. It was fairly brief. Right now, we can take any questions or any comments about things you've had experience with.
So, Gary, one of the listeners asked why they might have a high pH in a compost from 99% green waste.
We've been trying to figure that out up at Dickerson. You could have it if it's something where there's a lot of lime used on the turf, if it's turf grass. So it could be lime use getting into the feedstock. We think there's something else going on in some places where it's actually coming out of the compost pad with pad that's made up of asphalt, but over the years the surface of the asphalt has worn away and we're exposing carbonate gravel and crushed concrete as part of the asphalt mix. And that's another way that you can get a high pH where it's usually just green material. Those are the two I'm aware of. Are you aware of any, Greg?
Well, I would also ask what the so-called high pH is. It's not unusual to have pHs from 6 to the mid to upper 7s. So sometimes when we say that composting is a practice that results in a pH of around neutral, someone might think that high 7 might be too high. So I would only consider a high pH in your material is if you're into the 8s and above 8. If you're above 8, it's likely it's due to some concrete source, which carbonate, would have and some calcium oxides would have pHs above 8.2. But the person who did ask the question did mention that their pad is made from recycled asphalt pavement. So that's a possibility. There are a few other questions dealing with the problematic feedstocks. One person said they have a composting facility in Delaware that composts DAF, but they use a belt press to reduce the moisture to about 60% prior to arriving at the compost site. So that's more of a comment than a question.
That's a site I'd like to tour.
Yeah. So there was a previous question from your discussion on water management, wondering if there's any data or methods of calculation for how much contact water that would be generated from piles based on, say, the amount of a rain event and maybe the area of the compost facility and pad types.
Yeah, Jeff, that's an interesting question. I know that there's some of that data on individual sites, but I know of no place where there's a collection where you could make some generalizations. I don't know of a way to calculate that based on, the properties and the layout of the site. I guess we could look at layouts and do a little bit of hydraulic modeling on it. But off the top of my head, I'm not familiar with anything like that. Your site would actually have some of that data, I would think. You get a storm of X amount, you have some idea how much contact water your site generates. And we have some idea how much Dickerson generates and a few others. But each site operator is the one that has that knowledge. We'd have to collect it from a bunch of site operators, to the best of my knowledge.
Yeah, it seems like the type of feedstock and the orientation and size of the piles are going to play a large role in determining how much contact water is generated, how much is absorbed into the feedstock, and then the remaining amount that will run off. Yeah.
And we'll have drastically different amounts in the humid region compared to the arid region.
So we are running out of time. I want to thank everybody who has stuck around for this long. We can take a few more questions.
Gary, I'm going to go ahead and put the survey in chat just for the folks that are still here.
Okay.
Go ahead and take a moment. This doesn't mean you have to leave, but go ahead and fill out the survey for us.
Thank you, Mark. So if there are any other questions in the last couple minutes here, we'll be able to address those, but feel free also to contact Gary directly after the webinar with other questions. So someone else did compost that green waste will always have high pH right before it's mature. I guess it says it is a process point as I experience. So certainly the pH in the material will change during the composting process, and it may drop down from a higher pH as piles vent ammonia, for example, in the at the end of the active composting process. So it doesn't appear that there are any other questions coming our way. Again, I want to thank Gary for his presentation today. I'll let you know that by Thanksgiving, I will provide an announcement for our December composting webinar, which will be on odor management. That will be given by Craig Coker. So again, thank you everybody who tuned in for today, and have a great weekend and a wonderful Thanksgiving.
Thanks, folks. Bye-bye.
Bye.